Okay, Goldbach was a mathematician, and he had a certain conjecture that hasn't been proved or disproved to date. So let me just start by writing down an even number. 26. Can you express 26 as a sum of two primes? Is there a prime number and another prime number whose sum is 26? You should try to do that. Well, 26 can be written as 7 times 19, or 7 plus 19, so that we can write 26 as a sum of two prime numbers. What about 48? Can we write 48 as a sum of two prime numbers? Well, yeah. We could write 48, and you could try one. There are various ways to do it. How about 31 plus 17? Okay. Now 26 is 7 plus 19. It could also be written as 3 plus 23. Okay. We could start with the smallest primes. 3 added to 23 gives 26. 5 added to 21 gives 26, but 21 isn't prime. Next prime is 7, and you see you can add 19 and get 26. The next prime is 11, to which you'd have to add 15. That's not going to work. And the next prime is 13, to which you'd have to add 13. And the primes don't have to be distinct. So there are lots of ways to write 26 as a sum of two primes. Are there other ways to write 48 as a sum of two primes? Well, yeah, there are several. There are at least two, I mean. I'm not going to make a list, but it wouldn't be hard. Just following the same thing. 3 wouldn't work. 3 and 45 would be 48, but 45 is not prime. 5 and 48, well, that's 43. 5 from 48 is 43, so 5 and 43 give you 48. There's another pair, and there's at least another one. Okay. Now, question is, can this be done in at least one way? For every even number greater than 2. Because, of course, there's no hope as representing 2 as a sum of two primes. So very interesting conjecture that Goldbach conjectured, of course, that yes, it is possible, but that's only a conjecture. We don't know. Nobody's figured out a way to prove it. And of course, you can't just list all the primes or all the possible even numbers and see, because there are infinitely many of them. There's no way a listing would work. Don't mean to keep showing you the close-up of my hand, but that's the only way I can get this thing back into focus. Okay. Not the only way, it's the most convenient way. Twin primes. What do we mean by twin primes? Well, this is a pretty simple concept. Consecutive odd numbers that are prime, like 5 and 7, and 11 and 13, 17 and 19. These are primes that differ by 2. There are others. There's one less than 5, 7. You can probably discover that. And there are a bunch more. Now, nobody knows how frequent these are. Nobody knows if there are infinitely many twin primes, although it seems that there probably are. It seems likely, but nobody's been able to prove it. So, are these finite? Are they infinite in number? Here's a question. Can we have triplet primes, 3 primes in a row? Now, by 3 primes in a row, I mean 3 odd numbers in a row that are prime. Well, yeah, we can. 3, 5, 7. Okay? So there's one. Are there any others? Are they infinite? Those are two questions that we can answer. And you can figure out the answer to that. Now, I'm not going to tell you. I'm going to leave that as a mystery. Let's see if you can find any others. And if not, let's see if you can figure out why there aren't any others. Or if you do find others, is there some pattern to where they occur that tells you that maybe these things are infinite? Okay. Now, I never do know how to pronounce this guy's name. I've heard it mispronounced by many, many people. I know that I've heard it mispronounced by many, many people because I've heard many, many different pronunciations, and only one of them can be right. You can prove that logically, too, given my premises. Okay. So, I'm going to call him Fermat. Fermat's, he's French, and of course nobody except French knows how to pronounce French words. At least that's my perspective, being completely lost in French pronunciation. But Fermat's last theorem is fairly easy to understand. Okay, here we go. Let's say 3 squared plus 4 squared equals 5 squared. Can you verify that? Well, sure, that's fairly easy. 9 plus 16 is 25. Yep, it's true. Okay, let's see. 5 squared plus 12 squared is 13 squared. And that can be verified. Yep, that's true. Okay? It turns out that there are infinitely many we call these Pythagorean triples. Matter of fact, there's a formula that allows you to generate Pythagorean triples from any two integers, from any two whole numbers, counting numbers. Okay, so 3, 5, well, they're out of order, but 3, 4, and 5 are Pythagorean triples. 5, 12, and 13 are Pythagorean triples. Infinitely many others. Okay? Now, let's try it with cubes. Okay? We can add 2 squares to get another square, infinitely many different ways. Easily done. So, let's say, could it be possible that 22 cubed plus 31 cubed equals 37 cubed? Well, I haven't evaluated those numbers. I don't know. Actually, I do know. Because of Fermat's last theorem, I do know that this isn't true without even evaluating the numbers. Of course, I just made up those numbers, so it's unlikely that it would be true in any case, but at least this number is bigger than these two and it's plausible, except that it's impossible. You can never do this for cubes. A cubed plus B cubed equals C cubed never happens. Now, this was proved that you can't do this for cubes a long time ago. And the theorem wouldn't have caused all that much stir because I don't know the proof, but apparently it's not all that difficult to prove. It's been proved for hundreds of years. Now, Fermat, in his wisdom, and he was not a professional mathematician, but he was an avid mathematician, and probably certainly one of the best mathematicians of his day, if not the best. He was an exceptional mathematician, and he discovered and conjectured all sorts of things And he has a tremendous reputation, but most of his reputation is for his last theorem, which says that there are infinitely many triples, A, B, and C, that satisfy a squared plus b squared plus c squared, and everybody knew that back in Fermat's day. But that this never happens. And this never happens. And so on. For any n greater than 3, a to the n plus b to the n equals c to the n. Never. Forever. Okay, no other number but 2 has the property that you can put a triple down that satisfies this sort of equation for any whole number power of n, for any counting number power of n. This theorem was finally proved just a few years ago, and the proof of the theorem was actually excruciatingly complex. People tried, the best mathematicians, some of the best mathematicians in the world tried for years to prove this theorem. And they were able to prove it for 3, and I think for 5, and maybe for 4, and then for many other numbers. As a matter of fact, for even infinite classes of numbers, but never for all numbers. Until a guy named Weil finally beat this thing into submission a few years ago, and of course won wide acclaim. That's an interesting story in itself. There is a book about it, Proof of Fermat's Last Theorem or something like that. If you go to any bookseller on the web, you can find it very interesting. You can look it up. You can find that it's actually a very interesting story of what a mathematician goes through in trying to prove something of this magnitude.